So, welcome to my chapter on STP, Spanning Tree Protocol. First of all, I want to thank Rick Graziani for preparing these 168 slides for our CCNP switched networking course. This chapter is focusing mainly on the CCNP version 7 material. I've tweaked some of these slides so that they'll fit within our version 7 curriculum. So, without further ado, I want to discuss our topology that we're going to be using throughout our slides. And that is going to be this type of switched environment. Again, pay attention to the general architecture. We're going to have our single core switch, our distribution switch, and two access layer switches. Do not worry about downloading the packet tracer file within our current curriculum. We aren't using this. I've actually prepared this in a physical lab. Okay. With STP, it has been quoted that STP often accounts for more than 50% of the configuration and troubleshooting, as well as the maintenance headaches in a real-world campus area network, or CAN. It is a complex protocol that is very poorly understood. This is the person that was one of the primary developers of STP. I don't know how to pronounce her name. I keep butchering her name. But it is Redina Perlman. And it's really funny because I teach networking courses, whether they be Network Plus, any of the Cisco courses, Juniper courses as well. And STP is always one of those topics that a lot of people are very afraid of, even though it's not a complex topic. It's a complex protocol, and a lot of people, when they're going through their Network Plus or their Cisco CCNA or Cisco CCNP material, there's so much material, and STP is just normally, here it is, 1 week, 1 chapter, bam, that's it. And STP needs some serious in-depth thought. So without further ado, we're going to get into our basic STP. So, how to turn on spanning tree per VLAN. By default, STP is enabled on every port on the switch. But if for some reason STP has been disabled, which that's been fairly common in a lot of networks that I've reviewed, you can re-enable it. How we do that is globally. If you navigate to the global configuration on a switch, you can turn spanning tree on for an appropriate VLAN by spanning tree VLAN and an appropriate VLAN ID. If you want to turn it off, no spanning tree VLAN and that VLAN ID. But why would you want to do that? Here we have a pretty damn complex network. So, how do we use spanning tree to help in this network situation? Well, spanning tree will actually do loop prevention. This one is going to be IEEE 802.1d. This is legacy STP. It allows layer 2 devices to communicate with each other, as well as to discover physical loops in the network. It's an algorithm that creates a loop-free logical topology, and it can do this by disabling different links or putting them in a blocking state so that there can be no loops within our infrastructure. STP creates a tree structure of loop-free leaves and branches for the entire network. The question is, how does it do that? And that is the purpose of STP. STP answers the how it's done phase. So we've talked about in previous lectures redundancy. And one of the problems is when we do redundancy, redundancy can create loops. And that's one of the problems. So we want to do this in such a way that we control the looping on the network. So we can disable the appropriate interfaces while still leaving high-speed paths intact. So that's a key concept here, is we want to have redundancy, have high availability, have multiple pathways, but we want to control the way those pathways are utilized and brought down with STP. So layer 2 loops, broadcast and layer 2 loops can be a dangerous combination because we can end up with a broadcast storm, and our switches, if there's loops, will keep looping those broadcasts until the switch is overwhelmed and is brought down. Ethernet frames have no TTL field, meaning our broadcasts at layer 2 are infinite. After the Ethernet frame starts to loop, it will continue until a human prevents it. And that could be by breaking a link or turning off a switch. IP does have a mechanism to prevent loops. That's that time to live, that TTL. Bridge loops can occur anytime there is a redundant path or loop in a bridge network. Here, from this switch to this switch, it can just keep looping back and forth. The switches will flip-flop the MAC address tables entries, creating extremely high utilization within the CPU. I.e., we're going to be using all of the switch resources just to be flip-flopping those MAC address tables, again overwhelming those switches and bringing them to a crawl. Unicasts, unknown unicasts and broadcasts, have a very similar problem. So how do we prevent loops with STP? The purpose of STP is to avoid and eliminate those loops by negotiating loop-free paths to an elected root bridge. That root bridge is going to be the main switch for our dedicated traffic or for our high-speed traffic. STP determines whether there are loops and blocks links that are redundant based on certain criteria. For example, this may be a redundant link. That's a redundant link. It may shut down one of them. Because if they shut down this link, traffic will flow this way. So what we could do is we could turn off this link right here. Ensure that there is only one active path to every destination. So from this switch to this switch, it's going to use this link right here, and it's going to disable this path here. Though someone could argue, what about this path this way? That's coming up. Spanning tree algorithm. So what will end up happening is spanning tree will run a specific algorithm called spanning tree algorithm. And what that does is it starts disabling ports or blocking ports to prevent our loops. For example, here we have our 3 switches. This port right here is a direct path to our root, so it's going to move it into a forwarding port. This path is an alternative path or backup path, and so it's not the most direct route to our root bridge, so they could disable this port. If this port ever goes down, this link could be automatically brought up to start forwarding traffic this way. STA chooses a reference point, that's called our root bridge, then determines the available paths to that reference point. If more than 2 paths exist, STA picks the best path and then blocks the rest. But how is the STA, how does it perform its calculation? How does it know what's going to be the best path? How does it know what's going to be the reference point? The concept for our STP relies heavily on this thing called a root bridge. And that root bridge is based off of a bridge ID. So STP calculations make extensive use of two key concepts in creating that loop-free topology. That's going to be the bridge ID and the path cost. The bridge ID is going to be a combination of the bridge priority, or the priority of the switch, on top of the MAC address. So the bridge ID is going to be 8 bytes. 6 bytes for the MAC address, or 48 bits, and 2 bytes for the bridge priority. Next is this thing called path cost. This used to be the previous path cost. So 10 gig and 1 gig would have a path cost of 1. 100 megabit would be 10. 10 megabits would have 100 path cost. But they realized that with faster and faster links, if everything is going to be 1 for anything above a gig, this doesn't quite work. So they did a revised IEEE spec. So now 10 gig is represented by a path cost of 2. 1 gig is a path cost of 4. 100 megabits, path cost of 19, and 10 megabits, a path cost of 100. This is an important role when we start looking at our logical topology and our link speed for determining paths to our root bridge. So our bridge ID is used to identify individual bridges and switches. The bridge ID, or BID, is used in determining the center of the network in respect to STP. This is going to be known as our root bridge. The bridge ID without the extended system ID is going to look at just bridge priority and the MAC address. However, bridge ID with the extended system ID, adds this code for VLAN information, is going to be slightly different. It's going to use 4 bits for the bridge priority, so the bridge priority is going to go down some. The extended system ID is going to shift to 12 bits, and the MAC address will still be there. So here we're taking that bridge priority, and we're combining it, or separating it, so that we can have bridge priority and extended system ID. Those together are the same space as our 2 bytes. So here it is again. So this consists of 2 components. A 2 byte bridge priority, and the Cisco default is 32768, or in hexadecimal 0x8000. Usually expressed in usually expressed in decimal form, but sometimes you can see it in hexadecimal. And a 6 byte MAC address, which is expressed in hexadecimal. Each switch has a unique bridge ID because, again, it's based off of the bridge priority and MAC address. Within the original 802.1d standard, the BID was the priority field plus the MAC address field. All VLANs were represented by a common spanning tree. One spanning tree for all VLANs. We're going to talk more about that later. But what happens if you need per VLAN spanning tree? And that's what brought in the PVST, which requires that a separate instance of spanning tree is ran for each VLAN on each switch. More processing power. That's what it boils down to. So part of that PVST is we have to now have the BID require to carry the VLAN ID, or the VIDs. And that extended system ID will carry our VID. So our BID now is broken up into bridge priority and the extended system ID, which will carry our VLAN IDs. So what's the priority of one of our switches? So on In our topology on access switch 1, we're calling it access 1, we did a show spanning tree. Keep in mind our default priority is 32,768, and we're going to add that to the appropriate VLAN. So, here is our priority. Here is our system ID extended of 1. So that should equal a priority of 32,769. Because our extended system ID is part of VLAN 1. That's how we get our 1. We're going to add that to our priority, which will equal our priority. How do we do that for VLAN 10? Keep in mind that PVST is coming a little bit later. Same concept. We take the VLAN, that's equal our system ID. We're going to add that to our priority, and we're going to have that equal to our new bridge ID priority, because that is now 32,778, because our default priority of 32,768 plus 10. So what is the bridge, or the bid, of our core switch? Again, VLAN 1, we're going to take that, we're going to add that to our priority. So our new priority, it will be system ID 1 plus priority will equal our bridge ID of 32,769. And that will allow us to have a MAC address of 001C948A573. But you'll notice that is not the MAC address of our core switch. So we need to keep that in mind. So that was something to look at, because shouldn't our core be our root bridge? So we're going to be using our bid, our bridge ID, and that's used to elect a root bridge, and that's what's coming. Our lowest bid is the root. And you'll notice that our core doesn't have the lowest bid. So that means if all devices have the same priority, the bridge with the lowest MAC address becomes the root bridge. And that means that's not up to us. That's going to be how the switches do that election. So that's a problem. For simplicity in our topology, we will use the bridge priority without the extended system ID. It's the same process, we're just doing it per VLAN. Again, we've already looked at the original specs for path cost. Bridge uses the concept of cost to evaluate how close they are to the other bridges. We need to make sure that we understand the previous and the revised IEEE link speed values. It's used to create our loop pre-topology. The original 802.1d defines the cost as 1 billion divided by bandwidth of the link in megabits per second. That's how we got our 10, 100, and 1 gigabit links being the appropriate link speeds. But again, running out of room as we approached over 10 gigabits per second, we had to do our revised. However, IEEE has modified the most use a non-linear scale for our new values. These costs you don't really need to know per se, but do recognize that there are costs not just for 10, 1, 100, and 10 megabits, but there are for 4 megabits, 10 megabits, 16, 45, 100, 155, 622 megabits, 1 gig, 10 gig, and so forth. You may change the path cost by modifying the cost of a port. You have to be cautious when you do this. The bids and path costs are used to develop our topology. And again, hang on, we are getting close to that concept. So to create our loop-free topology, STP always uses the same 5 steps for our decision sequence. And that is Step 1, the lowest bid. Step 2, lowest path cost to root bridge. Step 3, lowest sender bid. Step 4, lowest port priority. Step 5, lowest port ID. Our bridges use configuration BPDUs during these 5-step processes. We assume that all PPDUs are configuration BPDUs until otherwise are noted. So the key concept for bridges are they save a copy of only the best PPDUs on every port. So when they make the evaluation, it's considered all of the BPDUs received on that port, as well as the BPDUs that would be sent on that layer or that port. As every BPDU arrives, it checks it against the 5-step sequence to see if there's a more attractive or lower value than its current existing BPDUs for that specific port. Because again, only the lowest value BPDU is saved. Bridges send configuration until a more attractive one is sent. So again, bridges save a copy of only the best. When making a decision, it considers all of the BPDUs received on the port, as well as ones that are sent on that port. As every one, it's checked against the 5 steps. It's looking for the lowest value. Only the lowest value is saved. Bridges send the configuration until a more attractive one is received. So let's see how this is done. So the STP algorithm uses 3 simple steps to converge on a loop-free topology. Step 1, elect a root bridge. Step 2, elect root ports. And step 3, elect designated ports. So step 1, when the network first starts, all bridges are announcing a chaotic mix of BPDUs. All bridges immediately begin applying the 5-step sequence. Switches need to elect a single or primary root bridge. Switches with the lowest bid wins. Note, many texts refer to the term highest priority, which is the lowest bid value. This is known as a root war. So, when the switches come online, there will be an election held for the root bridge. Remember, lowest bid wins. So who wins? Our core, which we've already looked at, shows a MAC address for our bridge ID as 0001C945A573. However, the root ID is a different MAC address. If we move to the distribution 1, we're going to notice that our bridge ID contains the MAC address of our distribution switch and the MAC address of our root ID. You'll notice that our root ID MAC address is not changing, but our bridge ID MAC addresses are. How we read this is the MAC address of the device we're looking at. This is our root bridge information. So here is our access 1 switch. Again, its MAC address, and again, that's the root ID or the root bridge's MAC address. Here we have access switch 2. Here is its MAC address, which you're going to notice is the MAC address for the root ID. So this is the root bridge because it used the bid and the lowest MAC address setting. So who won? That's the question. It will actually go, here's my bid and my MAC address, and they will all do it. And whoever has the lowest number will win. Turns out that access switch 2 wins. That may not be how we want it though. So here are just the bridge IDs. So let's look at some of our packet captures to see the appropriate input. So through our captured packet or captured frame, we can see there's the destination MAC address. So it's going to look for the protocol identifier, the protocol ID. It's going to look for the version. It's going to look for the message type. Because here are BPDU. It's a configuration type. Here's our version. Here's our protocol ID. The next are going to be the flags. The next, the root ID, the root identifier. The priority. Plus the extension. The root path cost. So the 2, we know that's a 10 gig connection. The bridge identifier, not just the root identifier, but now we're talking about the bid. That's going to be our priority plus our system ID. That's going to be, again, our appropriate VLAN. The port ID. The message age. The max age. The hello timer. And the forwarding delay. This is all done with BPDUs. So, the BPDUs are sent and relayed every 2 seconds with all of that information. And they're all going to send them to everyone. When the first booted root ID equals the bridge ID, that's going to show one of the that will show one of the items for our root bridge. At the beginning, all bridges assume and declare themselves as the root bridge by placing its own bid in the root bid field of the BPDUs. So they will all come in stating that they are the root. But again, it will actually look at the different fields of that configuration BPDU to figure out that access to is the root bridge. So once we have the root bridge, we'll transition into electing root ports. A bridge's root port is the port closest to the root bridge. It's heading traffic into the root bridge. Bridges use the cost to determine closeness. Again, we need to make sure that 10 gig, that 1 gig, we know those respective cost values. Every non-root bridge will select one root port. Specifically, bridges track the root path cost, the cumulative cost of all the links to that root bridge. So they'll use the path of, cost of the path, the bridge ID, and the port ID to determine that short or the lowest cost. So root bridge access 2 will send out a BPDU containing a root path cost of 0 to all of its interfaces. Access 1, distribution 2 will receive these BPDUs and add the path costs of their interface. we're going to assume that they have fast Ethernet, so that will change it to a link value or path cost to 19. So this value is used internally and used in the BPDUs to the other switches. So now that they know that these paths will take that appropriate path cost, we can start figuring out what ports that we want to keep on. So the difference for the path cost and our route path costs, the values assigned to each of the ports are added to the respective BPDUs on that port to calculate the route path costs. Again, it's cumulative. So we already talked about how these are 19. So what are the path costs for the route bridge for access 2? You're going to notice that these are all the interfaces that for access 2, and they're all in a forwarding state, and they're all part of a cost of 19. What about the path cost on distribution 1? It is actually going to disable gigabit 0/2. That's going to be an alternate or backup route, and it's going to be in the blocking state. And that's going to mean it's going to disable this link here. Because to get to the route bridge, again, this is a path cost of 19. To go through G0/2 to access the access 2 switch, it will be a 4. That's the link cost, plus 19. So to go this route, there'll be a cost of 23. So that is why that interface is turned off. And it will have G01, FA03, and FA05 all forwarding to access 2 switch. What about the path cost for access 1? It's actually going to forward out all of its interfaces to access this guy right here. It will actually send the cost to our access 2 switch. Okay, that will be a route port, while the other ones are designated ports. What about on distribution 2? It will show that the route port is going to be FA03, because that's going to be the port closest to the route bridge. And then it's going to disable 2 additional links, FA05 and GI01. It will disable those links because they're going to be alternate or backup routes, and the path cost to the access or to the route bridge is going to be higher. It will keep gigabit 0/2 open and in a forwarding state. That will be a designated port. Show. How do we see the spanning tree details? We can do show spanning tree detail on any of the switches. And you can see which ports will be the route port. You'll see the cost of those ports. So I guess the question here is, do we want it this way? And that's a key question for our STP. Again, we have our 19 because this link speed is going to be 100 megabit. This guy, its route port will be FA05, that's the forward-facing to the root bridge, it will have a path cost of 19, because again, it's 100 megabit. On our distribution, this is its forward-facing, or the root port. Okay, that's the forward-facing port to our root bridge. It will have a path cost of 19 because, again, it's 100 megabit. So you look at show spanning tree detail to see what information is there. The priorities, the root bridge, the flags, the timers, and all of that. A key thing to realize is if you do a show spanning tree detail, if you get no root ports showing up, that switch is the root bridge, because the root bridge will have no root ports. So switches will now send the BPDUs with their root path costs out of their interface. Access 1 uses their value of 19 internally and sends the BPDU with a root path cost of 19 out all other interfaces. Again, not out of its root port interface, all other interfaces. It will add the path cost of the additional links. Note that STP costs are incremental as BPDUs are received on a port. They are cumulative. So port or distribution 1 and distribution 2 will receive the BPDUs from access 1, add the new path cost of 4, because it's a gigabit connection. So the new root path cost is 23, 4 plus the original 19. Because remember, this path is 19, these paths are 4. So if distribution 2 wanted to access that switch port, or access the access 2 switch, if it sent it out GI or gigabit 01 to access 1, that will be a path cost of 4, plus we'll have to send it that way. That's a path cost of 19, so 4 plus 19 will equal that 23. However, both of these switches already have an internal root path cost of 19, so it will actually keep the lowest root path cost. That is why those interfaces will be turned down. So distribution 1 will now send the BPDUs with its root path cost out other interfaces. All of its different interfaces. So again, we're adding the existing 19 path costs, and we're going to add the additional path costs for the new links for the next switches. Here it's a gigabit, so 19 plus R4 is 23. This is 19. Here's a 100 megabit connection, so again 19 plus 19. This pathway will take 30. I have a path cost value of 38, and this way we'll also have a path cost of 4 plus an additional 19. So this one will be 23. STP costs are incremental, so keep that in mind. The final result will show the ports that will receive the root path cost plus the current path cost will equal the new root path cost. So what does that mean? That to go from this switch to our root bridge will be 4 plus 19. To go from this switch to this switch over here will be 4 plus 19. To go from distribution 2 to distribution 1 to the root bridge will be 19 plus 19, so that'll be 38. To go from our core either way to our root bridge will cost 23 because 4 and 19, or 4 and 19. So let's look at our spanning tree. Which port will be the root port? It has two equally path values, gigabit 01 and gigabit 02. So one of these will become the root port, one will become an alternate back port. Here it took G0/1, and it did that because typically it's going to take the lowest port. So why did it take that as the root port? And that is because the root path cost was 4. The root port is going to be 25. So next we will do elections for our designated ports. Same type of value will go out. So it will do our different elections for our root path. Again, heading to our root bridge. If I go to the core, it's going to cost 27. However, coming back, it's going to be 23. If I go through D2, it will cost 38. If I go through A1, it's going to cost 23. If I go through A2, it's going to cost 19. This will be the best path and the lowest path, so that will be the path it takes. If I go through the core, it costs, and so forth. It's going to ask the question, what is my cost to the root bridge? We have not discussed designation or designated ports just yet. We've only focused on our root ports. So every non-root bridge must select one root port. A bridge root port is the port closest to the root bridge. Bridges use the root port, path cost to determine its closeness, which we've already looked at. The core switch has two equally cost bridges. In this case, we need to look at the 5-step process decision again. Lowest bid, path cost, sender bid, port priority, port ID. So we'll actually look at the sending bid to see which is the lowest bid. Here we have a 0005 hexadecimal MAC. Here we have a 0060. So this is a higher bid. So this will use its lower path, or lower bid path. So the core will choose the root port of gigabit 01. Next, elect designated ports. The designated ports are a key thing here. The loop prevention part of the STP becomes evident during this step, electing our designated ports. A designated port functions as the single bridge port that both send and receive traffic to and from a segment and the root bridge. Each segment in a bridge network has one designated port, chosen based on the cumulative root path cost to the root bridge. The switch contains the designated port is referred to the designated bridge of that segment. To locate the designated port, let's look at each segment. The segment's perspective from the device. On this segment, which switch should I go through to reach the root bridge? Keep in mind, root path cost is the cumulative cost of all links to the root bridge. Obviously, the segment has not the ability to make the decision, so the perspective and the decision is then that of the switches on that specific segment. A designated port is elected for every segment. So a designated port is very similar to a root port in the fact that it's going to be a port on the switch, obviously. But the major difference is it is not going to be a forward-facing port to the root bridge. It is actually going to be the other side of it. For example, here is our root port. Here will be a designated port. So the root ports will plug into designated ports. The designated port is the only port that sends and receives traffic to and from that segment to the root bridge, the best port towards that bridge. The root path cost shows sent root path costs. This is an advertised cost in the BPDU by this switch at that interface, i.e., it's going to be the cost of reaching that bridge through me. A designated port is elected for every segment. The segment represents from a device of that segment which switch should I go through to reach my root bridge. I'll decide by using the advertised root paths. So what is the best path to the root bridge? 19 via access switch 1 or 0 via access 2. So what will happen is it will send it through access, or it will send it via the FA05 to access 2 via access 1's interface, because that's going to be the lowest path cost. So that will be my designated ports. So what about between distribution 1? Okay, that will be a designated port as well. Distribution 2, same thing. On a root bridge, all ports are going to be designated ports that connect to other switches. However, in other switches, non-root bridge switches, there will be one designated port. So, segment's perspective. Segment between distribution 1 and access 1 has 2 equal root path costs. Using the lowest sender ID, the first 2 steps are equal. Access 1 should become the best path and the designated ports. Again, here we're looking at our 5 steps. Lowest bid, lowest path cost to root bridge, lowest sender bid, lowest port priority, lowest port ID. So what is the best path to the root bridge? 19 via distribution 1 or 19 via access 1. They are the same. So who has the lowest bid? The port ID or the port priorities are the same, but you'll notice that the MAC addresses are not. So access 1 is the lower bid, so it will go this way. So access 1 has the lower sender bid. We can see that using Ethernet 02 of that VLAN, and so it is actually going to translate to a blocking port path because it will actually designate that as a blocking port with the path cost, because trying to get between the distribution to access 2, it will route through access 1, and we've already shown that that is the longer path. So that's something to consider. However, for our access 1, that gigabit interface, it's actually going to show a forwarding state. So it may be blocked on this side, but it's still forwarding on this side. Notice the designated blocking, designated forwarding. The designated bridge has that priority, and that will be the MAC address of our access 3. So, what about between distribution 1 and distribution 2? Using, again, the lowest sender bid, we're going to notice that distribution 1 has the lowest bid. So that will become a designated port. Same concept here. That will be forwarding, that will be blocking. That will actually be also known as a non-designated port, NDP, and it will not forward traffic out that way. What about between access 1 and distribution 2? Again, it will go through our lowest sender bid. Access 1 will be the lower bid, so that one will receive the designated port. Here on distribution 2, it will go to blocking state, and on the access will be a forwarding state. What about, because distribution 1 has the lowest path cost, it becomes a designated port. Because distribution 2 has the lowest path cost, it becomes a designated port. So which one is going to take it? They have equal path cost, they have equal cost to the root bridge. So they're both going to be designated ports, but this is going to lead to a problem. So all other of those ports that are not root ports or designated ports become non-designated ports. Non-designated ports are put into blocking mode. This will prevent our loops. No, one too many. So these will actually both be designated ports on the end. This will be a root port. So this will transition to a non-designated port. We determined this would be a designated port, so that will not be a designated port. So that will transition to a non-designated port. We can actually do a show spanning tree, and we can see all of the roles and all of the interfaces. So let's go through that. So on our core, we can see that gigabit 1 is going to be a root, gigabit 2 will be an alternate, and our root port will be in a forwarding state. On our distribution 1, our FA03 will be a root port, and our FA0/5 will be a designated forwarding port. And our GI, or gigabit 1, will also be a designated forwarding port. However, our gigabit 02 will be an alternate and will be in blocking. Our distribution 2, our FA03, will be a root and will be forwarding. Our FA05 will be showing an alternate blocking port. Our gig 1, same thing, it will be an alternate blocking port. And our gig 02 will be showing a designated port and forwarding. Our access 1 for our FA05 is a root port and forwarding. Our gig 1 is going to be a designated forwarding port. And our gig 2 will also be a forwarding and designated port. Lastly, our access switch 2, they will all be designated forwarding ports. Notice, none of these will be root ports. That's how you can determine if you have the root bridge or not. Okay, moving on. We're going to look through our packet frames. Again, we're going to look through the protocol ID, the version, the message, the flags, the root ID, the cost of the path, the bridge ID, the port ID, the message age, max age, hello timer, and the forwarding delay. You want to learn to be able to read this. It is that important. Okay, now let's get into the last two steps. Step 4 and 5. Lowest port priority and lowest port ID. So if we assume the path cost and port priority are the default 32, port ID is used in this case. So port 0/1 would forward because it's the lowest port. If the path costs and bridge IDs are equal, as the case of parallel links, the switch will go to the port priority as a tiebreaker. The lowest port priority wins. If all ports are set to default, which is 32, then it will go with the lowest port ID. You can change port priority. It can be between 0 and 63. If all ports have the same priority, the port with the lowest port number will forward the frame. So example, out of distribution 1, if they are dual links, FA0/3 will become the root port. And if we do a show spanning tree, FA04 should be in a blocking state. And it is. Because FA03, if it has the default priority number, then it will actually take the lowest link, which is FA03, and that moves to forwarding, and the secondary link will show blocking. So now let's talk about our per VLAN spanning tree plus. This maintains a separate spanning tree instance on each VLAN. PVST normally is only done over ISL, while PVST plus includes ISL and 802.1q. So this provides for load balancing on a per VLAN basis. Switches maintain one instance of STP for each VLAN on that trunk. Non-Cisco 802.1q switches maintain only one instance of spanning tree for all VLANs. So how we do that is we can set spanning tree VLAN, the appropriate VLANs, and then you can set the root primary for those appropriate VLANs. That way you can load balance between switches between VLANs. So if we're doing distribution 1, if we set that for the root for 1 and 10, if we set distribution 2 as the root for VLAN 20, it will load balance between the different VLANs. Notice that more links are being used, as opposed to having all of them managed. So let's do a convergence summary. The big thing is, for STP Convergence, the 3 steps. It must elect one root bridge, it must elect root ports, it must elect designated ports. Also, STP decisions are based on the following 5 steps. Lowest bid, lowest path cost to root bridge, lowest sender bid, lowest port priority. lowest port ID. Those are the 5 decision sequence steps that you need to know. In our example, with our 15-ish switches with 146 segments, with every switch port being a unique segment, it should actually yield 1 root bridge, 14 root ports, and 146 designated ports. Let's go ahead and get into our STP port states. Our 4 common ones: blocking, listening, learning, and forwarding. So blocking is the loss of our BPDUs detected, has a max age of 20 by default. Listening has a forward delay of 15 seconds. Learning has a forwarding delay of 15 seconds, and that transition to our forwarding. Remember, blocking moves to listening after it decides if it is a root port or a designated port, and that is determined when the link comes up. So our different port states. The first port state is disabled. It is administratively down and not a default STP port state. It will not send or receive BPDUs. It will not have MAC address updates. It will not send or receive data frames. And it is permanently down until someone turns it on. Our next state is blocking. And that will be if the port initialization happens, it will receive BPDUs only. It receives only. It doesn't send. It does not handle any updates. It doesn't send any data frames. And this will be continuous if a loop is detected. Next state is listening. It builds an active topology, thinks ports can be selected, either root or designated port. It will send and receive BPDUs. It will do no updates. It will do no data frame forwarding or sending. And it will actually forward delay of 15-second duration. It will return to a blocking state or an NDP if it cannot become a root or designated port. If listening can, it will transition to a learning state. And that will be building a bridge table. Switch can learn some MAC addresses, but it is not formally receiving frames in order to forward to them. So it will send and receive BPDUs. It will update its MAC address table, but it will not send data frames. And it will do this for a 15-second forwarding delay. Last state is our forwarding state. It will send and receive data if no loops are detected. Port is either a root or designated port. It will send and receive BPDUs. It will update our address or our MAC address table. It will send and receive data frames. And it will be continuous if there are no loops detected. So here is our little diagram for our standard states. Port enabled or initialized. Step 1. It may be transition into blocking initially. Step 2. Port will be disabled or failed. 3. Port selected as a root or designated port. 4. Port ceases to be a root or designated port. 5. Forwarding timer expires. The more Cisco proprietary is our port fast and our uplink fast. So this is what I mean by STP is complex. Let's talk about our STP timers. A hello timer is a timer between sending of a configuration BPDU by the root bridge, and its default is 2 seconds. Forwarding delay is the duration of listening and learning states, again 15 seconds, and the max age of the BPDU stored is 20 seconds. So again, our hello timer, that's the interval between configuration BPDUs. The hello timer value is configured at the root bridge, determines the hello timer for all the non-root switches. The locally configured hello timer is used for our TCN BPDUs. Our forwarding delay timer is a default value of 15 seconds and originally derived assuming a maximum network size of 7 bridge hops, a maximum of 3 lost BPDUs, and a hello timer interval of 2 seconds. We can see LAN switching by Clark or other resources for this calculation. Forwarding delay is used to determine the length for listening and learning states. Max age timer. Max age timer is the time that the bridge stores a BPDU before discarding it. Each port saves a copy of the best BPDU that it has received. If the device sending it the best PDU fails, it may take 20 seconds before the switch transitions the connected port to a listening state. So how do we modify timers? We can actually navigate to the global configuration, spanning tree, the appropriate VLAN, and you can set the forwarding time, the hello time, or max time. Here are definitions for all the optional STP time commands. Cisco recommends to modify the STP timer only on the root bridge. Also, the BPDUs pass these values from the root bridge to all other bridges in the network. It can take 30 to 50 seconds for a switch to adjust to a change in topology using our legacy STP. So again, configuring the root bridge, we can set the priority by spanning tree, the VLAN, the appropriate VLAN, priority, and then the number. The 1 and the priority are changeable, or you can manipulate. And again, the priority could be between 0 and 61440. The default is 32768. The lowest one becomes the root bridge. You can also force the switch to be the root bridge by issuing the command root primary. The spanning tree root primary command alters this switch bridge priority to 24,576 plus the VLAN ID. If the current root has a bridge priority which is more than the 24,000, then the current is changed to 4,096 less than the current root bridge. You can set a root secondary. This command configures the switch to be the secondary root in case the root bridge fails. The spanning tree root secondary will alter the switch bridge priority to 28,672. If the root switch should fail, the switch becomes the next root switch. So, changing the root bridge. If we modify the topology so that the core switch is the root bridge and the distribution 1 is the secondary root bridge for VLAN 1, we'd be changing it from the access to and changing it over to the core. So we'd issue the spanning tree VLAN 1 through 30 root bridge. And on distribution 1, would be setting a secondary root bridge. Would verify those changes by doing a show spanning tree, and so we could see the different root priorities and the appropriate bridge ID for those changes. So topology changes notification. This is going to be a specialized BPDU. This is known as a TCN BPDU, topology change notification. Direct topology changes is a change that can be detected on a switch interface which is an insignificant topology change like a user PC causing the link to go up and down, that's not a topology change. A direct topology change is a switch A detects that a link is down. It may transition that root port down, and it will remove the best BPDU from the root port, and it will also, obviously you cannot send a TC in out that port without some type of uplink fast or another path. So switch C is aware of the down link and sends the TCN message out to the root port. Root bridges send the configuration with the TCN bit set to let switches know the configuration change. Idle MAC addresses are then flushed, and switch A will actually wait to hear from our root through switch B, because this will be a blocking port, but it will still receive our configuration BPDUs, thus allowing that port to transition to the new root port, and it will go through the appropriate learning states. So the TCN does not start a STP calculation. So direct topology changes is a change that can be detected on a switch's interface. It can take about 30 seconds for the affected switch. But keep in mind, learning and forwarding, or listening and learning, 15 seconds each before it changes the forwarding delay. All switches will flush the idle entry in the MAC address. The solution is a uplink fast. We have not discussed uplink fast as of yet. We'll be doing that in our rapid spanning tree portion. An insignificant topology change, again, is a user PC going up and down. That's normal traffic. So no significant impact is given, and enough host switches could be a constant state of flushing the MAC address table. So that's why we don't do insignificant topology changes. Cause is an unknown unicast flood. So it would be a constant idle MAC address flush, a lot of resources. Oh, so I take that back. Sorry, our solution for that would be port fast. We're going to be talking about uplink fast, port fast, backbone fast here shortly. So to understand our spanning tree protocol changes, there's a nice little link to Cisco's website. But remember that a TCN does not start an STP recalculation. This fear comes from the fact that TCNs are often associated with unstable STP environments. TCNs are only a consequence of this, not a cause. The TCN only has an impact of the aging timer. And that is the first portion for our legacy STP. Now we're going to move into our next series for our advanced STP. Enhancements to 802.1d, that includes our PVST plus, our RSTP, and MST. Keep in mind, this is CCNP version 7 switch material. So, see the notes section for additional detailed information. And again, we are building off of our previous topology, except this time we're adding in some PCs. So the evolution of STP with our STP legacy 802.1d, that moved things into a common spanning tree or CST, also a mono spanning tree, also known as MST. Cisco's enhancement, the first evolution, was port fast, uplink fast, and backbone fast. Our rapid spanning tree, also known as 802.1W, was the edge fast, the Cisco port fast, uplink fast for RSTP, which is Cisco uplink fast, our backbone fast engine, also known as Cisco backbone fast. Other evolution developments for Cisco enhancements are our PVST, or per VLAN spanning tree. The original per VLAN spanning tree was only for ISL. PVST Plus is for both ISL and 802.1Q. It included previous enhancements as well as additional enhancements such as our BPDU guard and our root guard. Cisco's rapid spanning tree is Rapid Per VLAN Spanning Tree Plus. Cisco's MISTP uses PVST Plus. It includes all previous enhancements and is only really usable within the Cisco Catalyst 4000, 6000 series and above switches. Our new definition of MST is multi-spanning tree, which is different from our mono-spanning tree. Our multi-spanning tree is known as 802.1S, and it uses rapid spanning tree. So again, 802.1D, 802.1Q, 802.W, 802.1S. 802.1D focus on the media access of the MAC address bridges. 802.1Q is our virtual bridge LANs. 802.1W was rapid reconfiguration, support to 802.1D. Lastly, our multiple spanning tree, which was support to our 802.1Q. Other enhancements for our STP, again, port fast, BPDU guard, root guard, link fast, backbone fast. Per VLAN spanning tree or PVST plus, rapid spanning tree, RSTP, or our multiple spanning tree protocol. MST is also known as multiple instance spanning tree or MISTP, which that can be found for a Catalyst 6500 series switch and above. So let's get into the helping STP protect our LAN from problems. And we do that with things like port fast, BPDU guard, root guard, uplink fast, and backbone fast. So those are just some of the technologies dealing with our STP enhancements. So let's power cycle a host and watch the green lights. If we see this in Packet Tracer, we can see that it takes a little while for our switch to actually go active. So port fast. Host power is on, and the port moves from the blocking state immediately to the listening state. 15 seconds, typically. It determines where the switch fits into spanning tree protocol. After 15 seconds, the port moves from learning state. Another 15 seconds, the switch learns MAC addresses on that switch port. It will add all of the addresses it knows. After 15 seconds, moves to forwarding states. So that's 30 total seconds for the switch port to actually start allowing traffic flowing from that PC. But that's kind of a problem. So let's look at port fast with DHCP. The PC comes on, DHCP will send a discovery, but the switch is in a blocking state. Then in a listening state. DHCP discovery at this point has already timed out. The switch transitions to a learning state, and then a forwarding state. But again, DHCP discovery has already been timed out. The IP address for our newly powered on machine is a automatic private IP address, meaning it never gets an appropriate IP address. Also, insignificant topology change. A user PC causes a link to go up and down, normal booting or shutting down process, but that can trigger an insignificant topology change. No significant impact given unless enough host switches could be a constant state of flushing the MAC address table if they're constantly going up and down. This could cause unknown unicast flooding. So, port fast. The purpose of port fast is to minimize the time that access ports wait for STP to converge. When the port comes up, the port immediately moves into forwarding state. The advantage of enabling port fast is to prevent DHCP timeout. The PC power is on. The switch, as long as port fast is enabled, immediately turns to a forwarding state. The host will send the DHCP discovery. The host can now obtain a proper IP address information. So what you do on links that are connecting to hosts is you navigate to the appropriate interfaces, spanning tree, port fast. That way, those ports will be turned on with port fast. That way, those ports can take advantage of the port fast function. However, you don't want to enable port fast on uplinks to other switches. So port fast should only be enabled on ports that are connected to a single host, not switches. If a hub or switch are connected to the interface with port fast is enabled, temporary bridging loops could occur. If a loop is detected on the port, it will automatically move to a blocking state. So, again, power cycle the host with port fast enabled, you will see that instead of taking 30 seconds, it should populate very quickly. So our port fast will actually bring that link up real quick. So again, to configure our port fast, we can do it arrange and then spanning tree port fast. So if we want to see if our port fast is functioning, or if we want to verify port fast, we can do a show spanning tree interface, the specific interface, and the word port fast. And moving on, uplink. Uplink allows access layer switches the ability to converge quickly when a link is failed. Allows a blocked port on a switch to almost immediately begin forwarding frames when it detects the failure of a forwarding link. The uplink fast is designed for two only operation on switches that are leaves in nodes of the spanning tree. Uplink fast is not designed to use within the backbone or distribution. So with that said, leaves, they're on the end of spanning tree or in nodes. They are not to be used within the distribution or backbone area. That's why we have backbone fast. Uplink fast must have direct knowledge of the link failure in order to move a blocking port to a forwarding state. When access 1 detects a link failure on the current active link, the root port, again a direct link failure, uplink fast unblocks the blocked port on access 1, then transitions it to the forwarding state without going through the listening and learning state. The switchover occurs within 5 seconds. So if this link goes down, unblocking gigabit 1/1, and it will skip the learning and listening state and move directly to forwarding. If the root port fails, the next lowest path cost is unblocked and used without delay. Normally, the switchover occurs within a second, if done properly. So how we set up our uplink fast is spanning tree uplink fast. Uplink fast is enabled for the entire switch and all VLANs, and it is not supported on a per VLAN basis, meaning it is actually globally configured, and this is a feature not supported with Packet Tracer. Uplink fast keeps track of all possible paths to the root bridge, so not allowed on the root bridge. Switch's bid is raised to 49,152 to make it unlikely it will be a root bridge. Next, backbone fast. Similar to setting up our uplink fast, backbone fast is enabled globally. Backbone fast is a Cisco proprietary feature that's enabled switch-wide and saves the switch up to 20 seconds when it recovers from an indirect link failure. Configured in the global configuration mode and should be enabled on all switches in the network. Requires the use of a root link query request and reply, and disabled by default. So, this indicates a link to which the switch is not directly connected. An indirect link has failed, and the designated switch has lost a connection with the root bridge. When a switch receives an inferior BPDU, it indicates that the link to which the switch is not directly connected, i.e. an indirect link, has failed. That is, the designated bridge has lost its connection to the root bridge. Under normal STP rules, the switch ignores the inferior BPDU or the configuration max aging time. Link failures. Distribution 2 detects the failure as an indirect failure since it's not directly connected to that link. Distribution no longer has a path to the root switch. Backbone fast allows the blocked port on destination 2 or distribution 2 to move immediately to the listening state without waiting in the max age time for that port expire. Backbone fast then transitions the port on distribution 2 to the forwarding state, providing a path from distribution 1 to distribution 2. Normally, this will block it. However, with the inferior BPDU, it will know that this is no longer the path to the root bridge, so that should transition FA0/5 to a quick listening, and then change it to forwarding after the max age timer, thus restoring the path back to our root bridge. Backbone fast focuses on our root ID, cost of path, and bridge ID. An inferior BPDU identifies one switch as both the root bridge and the designated bridge. Distribution 1 is the designated bridge. It will normally send the BPDU with the root bridge as the core bid. However, with the inferior BPDU, a received BPDU that identifies the root bridge and the designated bridge as the same switch. I was only just the designated bridge, but normally that I can't get to the root bridge, so now I'm the root bridge as well. Is essentially what's happening. So protecting against unexpected BPDUs. Root guard, BPDU, loop guard, coast guard. Alright, so an unexpected BPDU. Enabling port fast can create a security risk in the switch network. A port configured with port fast will go into blocking state if it receives a BPDU An unauthorized device can send a BPDU into the port fast interface and then transition that port to blocking. When the port is in blocking state, it will accept all BPDUs. This could lead to false STP information being interjected. That enters the switch network and causes unexpected STP behavior. So that's a consideration. So from distribution 1, someone could plug in a switch into a port fast port, blocking and then listening occurs, and it will forward the BPDU to other switches. STP will reconverge, and this could lead to false information. Newly connected switch could advertise itself as the root port. BPDU guard developed to protect the integrity of the switch ports with port fast enabled, but also keeps and maintains STP integrity by disallowing unauthorized switches. So the solution would be BPDU guard. And how we do that is by turning on BPDU guard. When the BPDU guard feature is enabled on the switch, STP shuts down port fast, enables interfaces that receive BPDUs instead of putting them into a blocking state. Error disabled. The port must be manually enabled or automatically recovered via timers. So the BPDU would come into the distribution 1, and an error disable will shut down that interface, meaning no BPDUs will be sent or forwarded to other switches. Thus, the possibility for shutdown of or misinformation for STP is going to be more limited. Root guard. Root guard prevents a switch from becoming the root bridge, typically access switches. So root guard is used in the network if the network admin wants to prevent a switch from becoming the root bridge or from being a path to the root bridge. Root guard will be used to prevent switches from becoming that root bridge, configured on the switches that connect to this switch. For example, normally are access switches, configured on switches that connect to this switch. So how we do that is by navigating to the interface and turning on spanning tree guard, root. Root guard enabled on an interface applies to all VLANs to which that interface belongs. Do not enable the root guard on interfaces to be used by the uplink fast feature. With uplink fast, the backup interface replaces the root port in the case of a failure. However, if the root guard is also enabled, all the backup interfaces used by the uplink fast feature are placed into root inconsistent states, i.e. blocking. So the uplink fast must be disabled because it cannot be used with root guard. So, after the switch receives a superior BPDU, root guard puts the port into root inconsistent STP state. No traffic passes through that port in that state after the switch ceases to send sending superior BPDUs. The port is unblocked again via STP. The port goes from the listening state to the learning state and eventually transitions to the forwarding state. Again, recovery is automatic. No human intervention is needed. For example, if access 2 wants to become the root bridge, it will send a superior BPDU to our distribution switch. A STP inconsistent state will happen. No traffic is then passed. And what will happen is, it will be reconfigured. It will eventually transition to a listening and learning state, and then back to a forwarding state. So now let's look at Unidirectional Link Detection Protocol, or ULDP. An STP resolves redundant physical topology into a loop-free, tree-like forwarding topology. Meaning, the link between switch B and switch C will transition to a blocked port, or a non-designated port, which is again the default option of blocked. So our ULDP STP will use Bridge Protocol Data Units, our BPDUs, to send and pass information. No BPDUs will be received on our blocked interface. If a switch port in a blocking port stops receiving the BPDUs, STP eventually ages out the STP information for that port, again up to 50 seconds, moving it to a forward state. And will forward out BPDUs that transitions into a loop. This creates a forwarding loop or an STP loop. How is it possible for the switch to stop receiving BPDUs while the port is up? The reason is unidirectional links. With this example, no BPDUs is received, changing that state to a forwarding state. Part of RFC 5171, issues arise when, due to miswiring or to a hardware fault, the communication path behaves abnormal and generates forward anomalies. The link fails in the direction of switch C. Switch C stops receiving traffic from switch B. However, switch B still receives traffic from switch C. UDLD is a layer 2 protocol that works with the layer 1 mechanisms to determine the physical status of that link. So again, ULDP will auto-negotiate the configuration, speed, and duplex. When the UDLD switches share the device port ID, my device port ID and your device ID port will configure. Unidirectional links failure, meaning the link between switch B and switch C will go to a port disabled. So it should throw a unidirectional link detected on a specific port, and it will tell you port is disabled. The port shutdown by the UDLN remains disabled until either it manually re-enabled it or by the error disabled timeout expires if you've configured it. So configuring ULDL is a global configuration, and you can go to global configuration UDLM, either enabled or aggressive, or you can enable it per interface. And again, navigate to that interface, UDLM, enabled or aggressive. Normally, enable, the port is allowed to continue its operation and merely marks the port as being in an undetermined state and generates syslog messages. While aggressive mode, the port is placed in error disabled state and cannot be used. So there's different states depending on the options that you want. Loop guard. Loop guard also protects against ports that erroneously transitions to forwarding mode. Loop guard will also protect against STP failures, designated switches not sending the BPDUs due to software problems, and more. For example, switch B not sending it to switch C. If switch C does not get the BPDU from switch B, it will change to a forwarding state, i.e. cause a loop. With loop guard though, BPDUs, it should detect a unidirectional link failure, and it should get a loop guard block or an inconsistent blocking state error. If the switch begins to receive BPDUs again, it will transition through the normal STP states. Loop guard does not protect against problems due to wiring issues. Highest level of protection is to enable both loop guard and UDLD. How do we turn on loop guard? We can do it globally by doing spanning tree, loop guard default, or per interface. And that'll be navigate to the interface and spanning tree loop guard. Now let's go ahead and get into our rapid spanning tree, also known as RSTP or 802.1W. So the evolution of our STP, which we've already discussed, now we're moving into our rapid spanning tree protocol. So our RSTP allows for quicker convergence. Here we have 3 switches. We have our root bridge, we have our designating ports, our root ports facing it, and our designated ports, and then our alternative or discarding ports down here. The immediate hindrance of STP is convergence. That's been a huge issue. Depending on the type of failure, it takes anywhere between 30 to 50 seconds to converge to the network. However, with RSTP, this helps with the convergence issues that plagued our legacy STP. So STP versus RSTP is, first of all, RSTP is IEEE 802.1W standard. Numerous differences exist between both of them. RSTP requires full duplex point-to-point connections between the adjacent switches to achieve fast convergence. Half duplex denotes a shared medium, multi-devices. As a result, RSTP cannot achieve fast convergence in half duplex. STP topology changes take about 30 seconds. 2 intervals involved for the forwarding delay timer. While RSTP is proactive and therefore negates the need for the 802.1D delay timer, 802.1W supersedes D while still remaining backwards compatible. RSTP BPDU format is the same, except for the version number. RSTP spanning tree algorithm elects a root bridge in exactly the same manner. STP and RSTP also have the same port designation differences. RSTP has alternate and backup ports designations. Ports not participating in the spanning tree are known as edge ports. Edge ports become a non-edge port immediately if a BPDU is heard on that port. We have our non-edge port participants with our topology change notifications. The Cisco-based RSTP enhancements have these characteristics. They are integrated into the protocol at a low level. They are transparent. They require no additional configuration. They generally perform better than the Cisco 802.1D enhancement. BPDU carry information about the port roles. Because the RSTP and the Cisco proprietary enhancements are functionally similar, features such as uplink fast and backbone fast are not compatible with RSTP. That's food for thought. So RSTP can be applied on Cisco switches as a single instance per VLAN or rapid PVST+, multiple instances of our 802.1S, or also known as multiple spanning tree. So 802.1D ports are again that root port, designated port, and blocking port. The states are disabled, blocking, listening, learning, and forwarding. Well, RSTP, same election process as 802.1D, the lowest bid. The ports are the root port, designated ports, an alternative port, which is blocking. An alternative port receives more useful BPDUs from another switch, similar to how Cisco's uplink fast works. They also have a backup port, which is also blocking, and a port that provides a redundant but less desirable connection link. A backup port receives more useful BPDUs from the same switch it's on, and again is in a port block state. So let's look at our RSTP port states. First is discarding. It'll be for incoming frames are dropped, no MAC addresses are learned, combinations of 802.1d disabled, blocked, and learning. So our operational port states will be disabled or enabled and enabled. Our STP port states will be disabled, blocked, and listening, while our RSTP port states will all straight be discarding. While they're in the learning state, incoming frames are dropped, but MAC addresses are learned. So our operational state is enabled, our STP is learning, and our RSTP is learning. Lastly, forwarding. Incoming frames are forwarded, so we're going to get an enable for operational state, forwarding and forwarding for both STP states. This state is seen only in a stable active topology. The forwarding switch port determines the topology. Following a topology change or during synchronization, the forwarding of data frames occur only after the proposal and agreement process. RSTP BPDUs. Here's our STP ports and our STP port DPDUs. Here are our RSTP port states as well as our RSTP BPDUs. You're going to notice that in all states other than disabled, they're going to be sending and receiving our BPDUs. RSTP uses the same BPDU format for backwards compatibility, so they can coexist. BPDUs are sent out every switch port at hello timer intervals, regardless if the BPDUs are sent on that port. When 3 BPDUs in a row or 6 seconds are missed, the neighbor switch is presumed down. All MAC address information pointing to that switch or at that port is immediately aged out or flushed. Switches can detect a neighbor down for 6 seconds instead of a max age of 20 seconds. So for more information about RSTP convergence, you can check Cisco's website. Also, convergence is a two-step process. It will elect a root bridge, and it will examine all switch ports which by default are in blocking state, and advance to the appropriate state to prevent loops. The STP requires the expiration of several timers before switch ports can be moved to a forwarding state. RSTP takes a different approach. RSTP, when a switch joins the topology, i.e. is powered up, or detects a failure in the existing topology, it determines its forwarding decisions based on the type of port. It's an edge port, a root port, or a point-to-point port. An edge port is going to be a port on the edge. A non-edge port will be anything dealing with our environment. Edge ports will never have a switch connected to it, and so cannot form bridging loops. Immediately transitions to a forwarding state. Traditional identifies STP port fast features. For familiarity, the command for the same is spanning tree port fast. It never generates topology changes or TCNs when the port transitions to disabled or enabled status. An RSTP edge port is a switch port that is never intended to become connected to any other switch. The edge port again is very similar to port fast. Unlike port fast, an edge port that receives a BPDU immediately loses its edge port status and thus becomes a normal spanning tree port. In contrast, port fast, if a switch is connected to that interface when a port fast is enabled, it temporarily begins bridging a loop. Or they can occur at least. When the BPDU guard feature is enabled on the switch, STP shuts down that port fast port. Cisco's RSTP implementation maintains a port fast keyword for edge port configuration, thus making overall network transition to RSTP more seamless. If an edge port receives any BPDU, it will lose its edge port status. So a non-edge port. A non-edge port is one switch port on each switch that has the best route path closest to the root. A shared medium port link type. Things like our point-to-point port link type. That port operates in full duplex, connects to other switches, and will become a designated port. Uses a quick handshake with neighbors, switching rather than timers. Our shared medium port, or our link types, are port operating at a half duplex. It is assumed that that port is connected to a shared media, where multiple switches may exist. So that point-to-point, that quick handshake. Switch A connects to switch B through a point-to-point link. All ports are discarded or in blocking state. Switch A has a lower bid than switch B. Switch A sends proposal message or configuration BPDU to switch B. Propose itself as the root bridge. Switch B selects the new root port and the port from which its proposal message was received, and it immediately goes into forwarding state. Forces all non-edge ports to the discarding or blocking state. Sends an agreement message. Switch A immediately transitions its designated port to the forwarding state. No loops in the network are formed because switch B blocks all of its non-edge ports and because there is a point-to-point link between A and B. Switch C is connected to switch B. A similar set of handshake messages may occur. The proposal. Switch C will select the port connected to switch B as a root port, and both ends immediately transition to forwarding states. Handshake process continues throughout the topology, all the way through all attached switches. So RSTP, topology change notification. In the traditional 802.1d, if between A and C the root port goes down, the link between A and B was a NDP or blocking port. So the switch checks the status change up or down, and it will send the root bridge a TCN. The root bridge sends out a configuration BPDU to all switches to tell them about the change, 30 seconds before forwarding, and you'll notice here it will actually forward through B to A, thus changing that NDP to a new RP. With RSTP, detects a topology change only when non-edge port transitions to a forwarding state. RSTP uses its convergence mechanism, edge ports, point-to-point ports, and handshaking, etc., to prevent our loops. Therefore, topology changes are detected only so MAC address tables can be updated and corrected. This means that the loss of connectivity is not considered as a topology change anymore, contrary to the 802.1d. That is, a port that moves from blocking no longer generates a topology change notification. So RSTP topology change notifications. When a topology change occurs, switches flush the MAC address associated with all non-edge ports. Switches send a BPDU with the TCNs. Bits set to all neighbors so that all of the neighbors can update the MAC address tables too. When the bridge receives a BPDU with the TCNs bit set for a neighbor, it clears the MAC addresses learned on all ports, except the one port that it receives the topology change. It sends the BPDU with the TCN on all of its designated ports and root ports. Keep in mind, RSTP no longer uses specified TCN BPDU unless a legacy bridge needs to be notified. This way, the TCN floods very quickly across the whole network, now a one-step process. The initiator of the topology change floods this information throughout the entire network, as opposed to the 802.1d standard, where only the root bridge did. Much faster, which means the wait for the root bridge to be notified and the max age plus for its delays. In just a few seconds or a small multiple of hello timers, most of the entries in the CAM table for the entire network should be flushed and corrected. This approach results in a potentially more temporary flooding, but on the other hand, it ceases the potential state information and allows for rapid convergence. How do we enable it? Cisco has implemented the RSTP with rapid per VLAN spanning tree. So how you do that is by globally configuring spanning tree mode rapid PVST. To revert back to the default PVST, you can use a traditional PVST instead of rapid-PVST. So to configure the RSTP edge ports, you can actually just do the interface that you want to go to, and you're going to configure it as a port fast port. RSTP automatically decides if a port is point-to-point and if it's in full duplex or half duplex. So if you need to set it manually, other switches in half duplex but still point-to-point, by the way, both ends must have the duplex speed. Spanning tree for that appropriate interface, link type, point-to-point, will configure that point-to-point link. So let's look at our spanning tree enabled protocol, or our rapid spanning tree protocol. So we've already discussed our first evolution in STP. We've already talked about our Cisco Enhanced second evolution, and that is our PVST and RPVST. And if there are more than 500 VLANs in the network, that would be 500 instances of STP running. That's kind of unrealistic, because there's going to be a version of spanning tree per VLAN. So PVST does allow different VLANs to have different root bridges, which can allow for the use of redundant links. But what about the Cisco MS STP, or the use of that for the per VLAN spanning tree plus? So part of that multi-spanning tree protocol, or 802.1s, or MSTP or MTP, is going to be used for our Cisco Catalyst 6500 series switch or above, which we've already discussed. We can have several different instance maps to the appropriate VLANs. Multiple spanning tree will extend the 802.1w RSTP algorithm to multiple spanning trees. The main purpose of MSTP is to reduce the total numbers of spanning tree instances to match the physical topology of the network, thus reduce the CPU cycles, allow the network admin to configure the exact number of instances. PVST runs a single instance of STP for each VLAN and does not take into consideration the physical topology. We may have 1,000 VLANs, but only 2 different topologies, i.e. 2 different root bridges. So PVST will still create 1,000 instances of STP. So MST, on the other hand, will use the minimum number of STP instances to match the number of physical topology present. So may have 1,000 VLANs, but only 2 different topologies, thus MSTP will only let you have 2 instances of STP. So MST regions. An MST region is a group of switches placed under a common administration like an AS. The main enhancement introduced by MST is the ability to map several VLANs to a single spanning tree instance. This raises one problem, however. For determining what VLAN to be associated with what instance, based on received BPDUs, devices need to identify these instances and their VLANs. So details are not super important, but each switch that runs MST in the network has a single MST configuration that consists of 3 attributes. Those attributes are an alphanumeric configuration name, 32 bytes, a configuration reversion number, 2 bytes, a 4096 element table that associated with each of the potential 4096 VLANs supported on the chassis of a given interface. In the most networks, a single MST region is sufficient. A single MST region can handle 15 STP instances, or topologies. Within a region, all switches must run the same instance of MST, as defined by the MST configuration name, MST configuration revision number, and MST instance to VLAN mapping table. MST was designed to work with all forms of STP. IST, internal spanning tree instance, runs to work out a loop-free topology inside of the MST region. ISTs represent the entire MST region as a single virtual switch or bridge to the common spanning tree or 802.1d outside. Wow, half love these acronyms. So many. Our MST, remember that the whole idea of MST is to map multiple VLANs to a smaller number of STP instances. Cisco supports a maximum of 16 MST instances of MST IS in regions. The IST uses MST 0, leaving 1 through 15 available for use. The distribution 1 switch is the primary root bridge for the data VLANs 10, 30, and 100, while the second root bridge for voice VLANs 20, 40, and 200 exists. Distribution 2 switch is the primary route for those 20, 40, 200 secondary root bridge. So, what we can do is we can assign distribution the primary for its 3 and a backup for 20, 40, 200. While in distribution 2, we can set the primary for 10, 40, and 200 and have a secondary root bridge for the data VLANs 10, 30, and 100. So how do we do that? We can do that by globally configuring spanning tree in MST mode. Once we do that, we can actually go to the MST configuration. You give it a name, a revision number, and the different instances, 1 and 2, and the appropriate VLANs. Once we do that, we can actually set the different instances for what bridge. So we can actually change it so that the first instance will be the primary route. We can set the second instance to be a secondary route. On our distribution 2 switch, same thing, except we're going to flip-flop those so that instance 2 will be the root primary and the 0 through 1 will be the root secondary. So for complete configuration guides for our PVST to our MTST, double check Cisco's website. Keep in mind, if we want to verify MST, we can do a show spanning tree, and we should actually get a MST version. I wanted to thank you for this. Hope you guys have a great day.